Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210 Introduction to the Sky and Solar System, Lecture 3, How the Sky Appears to Us. So in our last lecture, we took a tour of the universe, and in this lecture, we're going to go back to looking at the night sky and the day sky for that matter, and see how they look to us, and talk a little bit about how we measure the positions of objects in the sky. So first of all, let's talk about how the sky appears. We all know that the Earth is rotating on its axis, and it rotates once every 24 hours, and this is what gives us day and night on the Earth. Day on the Earth is simply when we are on the side of the Earth facing towards the sun, and night, of course, is when we are on the side of the Earth facing away from the sun. I think it's worth pointing out, because we don't often think of it this way, is the reason that the sun disappears at night is not only that the Earth is blocking the sun from view, but that we happen to be inside the shadow of the Earth. And this will become a little bit more important later on when we talk about eclipses, particularly solar and lunar eclipses, to just remember that it is when it is nighttime outside, it is because we are in the shadow of the Earth. The Earth is blocking the sun from view. So this diagram shows us a person on the Earth at 4 times of day. So this person right here, it is the middle of the day, so that is noon. This person is located at sunset, midnight, and of course sunrise right here. And during the course of the day, the Earth's rotation carries you around like this. Now, most of us don't like to think of ourselves moving like this. Most of us like to think of ourselves as sitting still. As the Earth turns, and we rotate around with the rotation of the Earth, it causes everything in the sky to move. And what we usually think of, instead of everything in the sky sitting still and we're the ones moving, we usually picture the opposite. We usually picture ourselves sitting still, and we think about everything in the sky moving. So this is a picture taken from the big island of Hawaii. This is a picture taken from Mauna Loa looking towards Mauna Kea. Off in the distance here, this mountain is actually Mauna Kea. It's a dormant volcano. Located on top of Mauna Kea is a major observatory. It's got some of the largest telescopes in the world there. And in this direction, we are facing towards the north. And if we look at the stars over the course of a few hours, it looks like the stars are moving. This is a time exposure where the shutter on the camera was left open for a few hours so that you could actually see the motions of the stars during those 2 hours. And during those 2 hours, the stars were rising in the east, moving across the sky, and some of them were setting over here in the west. And all of them appear to be circling around a point in the sky that, as we will see later on, is the North Pole in the sky, the North Celestial Pole. So that is how the sky appears to us. The sky appears to be constantly in motion as the Earth is turning. Everything, the sun, the moon, the planets, the stars, are rising in the east and setting in the west because the Earth is turning from west to east. Now, a great way to see this as well, and to see how we view the sky, is to use a planetarium program like Stellarium. Stellarium is my favorite planetarium program, and it's my favorite for 2 reasons. I think it provides a beautiful view of the sky. It's really easy and intuitive to use, and most importantly, it's free. So you can download it for either a Windows machine or you can download it for a Mac. They have both. They also have it for Linux if you have a Linux machine. But let me demonstrate Stellarium here for a second. Stellarium, as I said, is a great planetarium program. When you open Stellarium, this is what Stellarium looks like. So, inside Stellarium, we have a horizon that cuts across the middle here. We'll talk more about that in a second. We've got a date and time window that shows us what the current date and time is. And if you look down there in the lower left-hand corner, you will see the location. It's telling me that the field of view right now, or the view that I'm seeing, is for Charlottesville, Virginia. It is on June the 14th, 2020, and it is set for 4 p.m., 1600 hours, 4 p.m. in the afternoon in Charlottesville, Virginia. Now, there are lots of cool things you can do with Stellarium. Right now, I've got time turned off, so you'll notice that the clock is not moving forward. If I go down here to the very bottom, there are all these controls. I will unpause it, and I will now let time move forward. So if we look at this clock here on the date and time clock, we will see now that it is 1600, 4 p.m. and 10 seconds, 11, 12, 13 seconds right there. So we can see time moving. Now, of course, time is moving at its regular pace right now, so you don't really notice the sun moving. Inside Stellarium, I can actually come down here and I can use this button to speed time up a little bit. And if I speed time up now, you'll notice the time is moving much faster. And if I click it one more time, you'll see that it's moving fast enough that now you can actually see the motion of the sun in the sky. So we very quickly there went from 4 o'clock in the afternoon. It is now 6:17 in the afternoon. I have slowed down time so that it's moving at its regular pace. But in that time, in that course of a few hours, you saw the sun move across the sky. Now, what's interesting is we talk about the sun moving across the sky, but of course the sun is sitting still. What's really happening is the earth is rotating. But again, we think of ourselves sitting still and we talk about the sky as if it's moving. A couple of other things that I will show you in Stellarium before we go back to the day-night sky is if I come very far over here on the left-hand side, just come over to the left-hand margin, I will see all these menus that appear. The top menu is my location window. It's how I can change my location. So you can just simply type in Charlottesville, and you will see it come up with Charlottesville. You can type in pretty much any location on Earth, any big location that has lots of people, and it will show up on the map, and you can select that. Just simply click on it to select it, and if you look in the lower left-hand corner, you can confirm that it has got the right location. Also over here on the left-hand side is this date and time window. So when I click that, it brings up today's date and the time, and I can set Stellarium for any day or any time, thousands of years into the past or thousands of years into the future. And then there are all kinds of other settings that you can change over here to display how the sky looks. We'll go over some of those later on as we go through different lectures and need them. But right now I want to talk about how the sky appears. So if I start moving time quickly again, I will let the sun set, and as the sun sets over our horizon and it gets dark, you will see the stars come out at night. And you can see the stars there. And we can look in different directions. If I just take my mouse and click, I can click and drag the sky around so that I can see this is what the view looks like facing south. There are Jupiter and Saturn up there in the sky. Here's what I see facing towards the east. And then, of course, if I face towards the north, there's the Big Dipper, and the two pointer stars point to the North Star Polaris up there in the sky. And this is tomorrow morning with the sun rising over here in the east. And now we will cycle back to the western sky. So that is a little introduction to Stellarium. Let me pause this for right now. We'll come back to this later on. But let's go back to our lecture. So that is how the sky appears to us. It is useful, and astronomers still think of the sky as a giant dome over our heads. I think it's really interesting that it is now the 21st century, and we've known for a long time that the sky is not a dome over our head with the sun, the moon, and the stars and the planets painted on that dome. And even though we know that that is not what the sky is, astronomers still think about the sky as a dome over our heads. And the reason we think about it this way is that it's sort of the natural way to view the sky. And so very often this semester we will be talking about the sky as if it was a dome located over our heads, with all the stars painted on the inside of the dome, the sun, the moon, the planets moving on the inside of the dome, kind of like being in a planetarium theater. The truth, of course, is that the stars are scattered throughout the universe. They're not painted on the inside of a dome. The planets are all at varying distances. The sun and the moon are at varying distances from us. And everything that we see going on this dome, for example, rising in the east and setting in the west, is actually caused by the rotation of the earth. But we're still going to talk about the sky as a dome. And so let's talk about two important places on this dome. The first one is the zenith. The zenith is the point directly over your head. Okay, so the zenith is the point straight overhead. The nadir or nadir is the point straight below your feet, N-A-D-I-R. If you're into crossword puzzles and you need to know the point below your feet is the nadir, and the zenith is the point straight overhead. As the dome turns, as the earth turns, as the earth rotates, this dome appears to turn over our heads. As the earth rotates from west to east, it makes everything in the sky looks like it's going east to west. Now, another important place on this celestial sphere is the horizon. The zenith is the point straight overhead. The horizon is where the dome of the sky meets the ground. And the horizon surrounds us, 360 degrees of horizon all the way around. Now, we get various horizons. If you are out at sea, you get a perfect horizon. So this is an image of the horizon out at sea where you can see the water and you see the very crisp, perfectly straight line that divides the sky from the earth. Most of us, though, don't have a horizon like this. Most of us don't have a nice, flat, straight horizon. Most of us, especially in this area, have something like this. We've got buildings or trees or mountains in the way, and the true horizon is off in the distance somewhere, hidden behind the mountains. In this class, whenever we talk about the horizon, we're going to be talking about the true horizon and not the apparent horizon that you might have at your location. So I might tell you that the sun is 20 degrees above the horizon, and what I mean is if you were in a ship at sea, if you had a perfectly flat horizon, the sun might be 20 degrees above that horizon. So the horizon is where the dome of the sky meets the earth. Okay, let's talk a little bit about how we measure things in the sky. The first way that we measure things in the sky is we can talk about linear measurements of things. This is the actual size of an object. So we can talk about the fact that the sun is about 900,000 miles in diameter. Or we can talk about the fact that the moon is just over 1,700 kilometers in radius. So these are physical sizes of an object, and they're measured in meters and kilometers. The problem with linear measurements is that when I look at something in the sky, I can't tell how big it is in miles or kilometers or astronomical units, any of these physical measurements. In fact, when I look at the sun and the moon in the sky, they both appear to be about the same size. And that's through an interesting coincidence that the sun is about 400 times bigger than the moon, but it's also about 400 times further away than the moon. And that means that although the sun is much bigger than the moon, it appears to be about the same size as the moon. So just looking at the sky, I can't tell what the linear measurement is. What we do in astronomy instead is we talk about angular measurements. An angular measurement is the apparent size of an object. It's not the true physical size, it's how big it appears to us. And the unit of measurement we use for this is degrees. We clearly can't use miles or kilometers because just when I look at it, I can't say, well, it looks to be a mile across because that isn't really meaningful. To say that something looks to be a mile across, or to look at the moon in the sky and say, oh, well, it looks to me to be 2 inches across, because 2 inches, if I view it up close, it's really big. If I view it very far away, it's very small. And so that's why astronomers use angles instead. Now, we all know that a circle is divided into 360 degrees of arc, and so we use those degrees of a circle for measuring angular sizes of things. The thing to know about the angular size of an object, it doesn't give you any indication of the actual size of the object. It could be a very big object seen very far away, so it looks small, or it could be a small object up close. You really can't tell. The apparent size of an object depends on its distance. An object that's really close to us will appear bigger, and an object that is farther away from us will appear smaller. Now, there are a couple convenient ways to measure angles in the sky. It turns out you were equipped with a fairly nice protractor, and that protractor is your hand. It turns out your finger, when you hold it up at arm's length, is about 1 degree across. So if you take your finger and hold it out at arm's length, that is, stretch your arm to its maximum length and look at your finger is about 1 degree in size. And this works out because those of us that have bigger than average fingers tend to have longer than average arms. And those of us with smaller than average fingers tend to have shorter than average arms. And so for the average person, your finger turns out to be about 1 degree. Your fist held out at arm's length is about 10 degrees across. And if you extend your hand like this, from the tip of your thumb to the tip of your pinky, from the tip to tip, held out at arm's length, is about 20 degrees in the sky. So let me give you an example of this. If I wanted to start on the horizon and measure to my zenith straight overhead, if you just look at the way my arms are oriented right now, you'll notice that it's a right angle. You can probably guess that that's 90 degrees. From my horizon to my zenith is an angle of 90 degrees. So let me measure it. And I'm going to start with this one. So if I hold this out at arm's length, that's about 20, 40, 60, 80, and then I make a fist to get another 10 degrees up there, and that is how I measure angles in the sky. Okay, so I had 20, 40, 60, 80, but to get to the zenith, I have to go another 10, and so I measure from my horizon to my zenith an angle of 90 degrees. In the sky, the sun and our moon each appear to be about half a degree in size. And so that's how big they are. They're about half the width of your finger held out at arm's length. So if you hold up your finger at arm's length, it will easily cover up the moon. It will easily cover up the sun. Now, one problem we have in astronomy is that degrees are a little too big. We need to divide degrees into smaller units. Nowadays, astronomers often divide degrees into decimal degrees. So you could have something that is 5.2 degrees across or 5.217 degrees across. But we often in astronomy use an old system for dividing degrees, and you still see it in astronomical coordinate systems today, which is why I want to mention it now, that we use an old way to divide angles, and that is dividing an angle into minutes and seconds of arc. Angles in astronomy are often measured in degrees, minutes of arc, some are often called arc minutes, and seconds of arc, often called arc seconds. A degree is divided into 60 minutes of arc, or 60 arc minutes. An arc minute is divided into 60 seconds of arc, which means a degree has in it 60 arc minutes, and each of those arc minutes have 60 seconds. And so a total degree, one degree, has a total of 3,600 arc seconds in it. Now, this isn't that bad of a system to remember, because if you've been using something like this your whole life, 1 hour is divided into 60 minutes. 1 minute is divided into 60 seconds. We do the same thing with degrees. In fact, we get it from the same system. You can thank the ancient Babylonians for this system where we divide time into 60ths and we divide angles into 60ths. So my finger at arm's length is a degree. If I divided it into 60 parts, each part would be an arc minute. And if I divided each one of those into 60 parts, each one would be an arc second. An arc second, or a second of arc, is a really small angle. To give you an idea of how small an angle it is, an arc second is the size of a U.S. quarter as seen from about 3 miles or 5 kilometers away. Imagine that I took this quarter and I walked 3 miles away from you and I held it up. Now you can imagine if I walked 3 miles away from you, I would look like a little tiny spot. And this quarter is even smaller than that. In fact, you probably couldn't even see the quarter. Well, you couldn't see the quarter without a telescope, but that quarter would be about 1 arc second in size. Okay, so that's how we divide angles in astronomy. So let's put this to use with a learning catalytics question. If I hold a quarter out at arm's length, it appears to be about 3 times larger than the sun, which is half a degree across. Washington's nose on the quarter is about 1/12 the diameter of the quarter. So if Washington's nose is 1/12 the diameter of the quarter, and the quarter is 3 times the size of the sun, what is the angular size of Washington's nose on a quarter when I hold it at arm's length? And I want the answer in minutes of arc, or in arc minutes. So take a few minutes, work this out. So now is a good time to go ahead and pause the video. Stop the video, go into Learning Catalytics, answer this question in Learning Catalytics, and when you come back, I'll give you the answer. Okay, Now that you've had the chance to work out this, let's talk a little bit about the answer to this one. How large is Washington's nose on a U.S. quarter held at arm's length in minutes of arc? Well, I said that the sun is half a degree in size. A degree is 60 minutes, 60 arc minutes. So half a degree is 30 arc minutes in size. So the sun is 30 arc minutes in diameter. I said that the quarter was about 3 times the diameter of the sun. So if the sun is 30 arc minutes across and the quarter is 3 times that diameter, that means that the sun is 90 arc minutes in diameter. And I said that Washington's nose is 1/12 the diameter of the coin. So if the coin is 90 arc minutes across and Washington's nose is 1/12 of that, Washington's nose is 1/12 times 90, or 90 divided by 12, which is 7.5 arc minutes in size. So when I hold up a quarter at arm's length, Washington's nose is 7.5 arc minutes in size. So to talk about angular sizes of things in the sky, we've already mentioned that the sun and the moon are each about half a degree in size. If you find the Big Dipper up there in the sky, the 2 pointer stars that point to the North Star Polaris are about 5 degrees apart from one another. And so those are just a couple more examples of angular measurements in the sky. So now let's talk about how we talk about where something is located in the sky. And there are 2 numbers that we use, that astronomers use, to designate the location of something in your local sky. And those are the altitude and the azimuth. The altitude of something is simply the height of a star or the sun or the moon above your true horizon. We call that the altitude. It's easy to remember, right? The altitude of an airplane is how high it is. The altitude of an object in the sky is how high it appears in degrees above the horizon. We start on the horizon and we go upward from the horizon to measure the altitude of an object. So, for example, here's a woman standing on the surface of the earth. There's the zenith, the point straight overhead. Here is her horizon surrounding her right there. And we've got the sun up there in the sky. And the question is, what is the altitude of the sun? Well, the altitude of the sun, in this case, we start on the horizon. We measure upwards from the horizon. We measure this angle, and we see that in this particular case, the altitude of the sun is 60 degrees. That means it is 60 degrees above the horizon. So that is the altitude of an object. Now, the problem with altitude is I have to tell you which direction to face. So, for example, if I told you that the sun was out there at an altitude of 60 degrees, you wouldn't know whether to face east or south or west. So we have to designate a second number, and that second number is called the azimuth. And azimuth is the direction that you face with respect to true north. So true north is defined to have an azimuth of 0 degrees. East is 90 degrees, south is 180 degrees, and west is 270. So remember, you never eat soggy waffles from elementary school, right? North, east, south, west. North is an azimuth of 0 degrees. East is an azimuth of 90. South is an azimuth of 180. West is an azimuth of 270. And it brings me back to north. You can think of it, and in fact it really is, the points on a compass. North is 0. And then we have 10 degrees, 20, 30, 40, 50, 60, 70, 80, 90 until we get to east. And then you count up until you get to 180, which is due south. And you continue around the compass rose or the compass circle. Always remember that wherever you are on Earth, north is always an azimuth of 0 degrees. South is always an azimuth of 180 degrees. East is 90, west is 270. Okay? So let's put this to use for a second. I showed you this diagram a second ago, and in that diagram, we said that the altitude of the sun was 60 degrees right here. The question I have now is, what is the azimuth of the sun in degrees? In this particular diagram, you can see that the sun is in the southeast. In fact, it's exactly in the southeast. So the question is, what is the azimuth of something in the southeast? So take a moment, go to Learning Catalytics and answer this question inside Learning Catalytics. What is the azimuth of the sun in this particular case? Okay. Let's talk about what the azimuth is. So remember, the azimuth of an object, we start at north and we measure around the compass rose. So north is 0 degrees. This would be 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees to get to due east over here. 100, 110, 120 going around to south over here. The sun in this particular case is in the southeast. It is exactly halfway between south and east. Well, the full angle between east and south is 90. East is at an azimuth of 90, south is at 180, so the angle between the two of them is 180 degrees. Is 90 degrees. Half of 90 degrees is 45. So the azimuth of the sun in this case is the azimuth of east, which is 90, plus another 45 degrees. So the azimuth is 135 degrees. The azimuth of the sun in this case, southeast, is 135 degrees. Now, the problem with altitude and azimuth is that they change throughout the day. So let's take a quick look at the sun for a second, and let's talk about the sun moving across the sky. So here's Stellarium again. Let me see, we've got it set for, let's go back to the 14th, and let's set it for the evening. Let's go back to 4 o'clock in the afternoon. Okay, there's the sun at 4 o'clock in the afternoon. The altitude and the azimuth of the sun are constantly changing. You can imagine that when the sun is on the horizon, because we measure altitude from the horizon going upwards, that when the sun is on the horizon, when it rises first thing in the morning, its altitude is 0 degrees. And then it gets higher and higher throughout the day until at astronomical noon, it reaches its highest. And then afternoon, it gets lower and lower and lower until when it sets in the evening, it's once again at an altitude of 0 degrees. So the altitude of the sun is changing. It starts at 0, gets to some maximum altitude, comes back to 0 again. The azimuth is also changing. Around the time of the equinoxes, the sun rises due east and sets due west. So first thing in the morning, when the sun rises, its azimuth is 90 degrees. When the sun is highest in the sky at astronomical noon, it is 180 degrees. It is due south. And the azimuth when the sun sets in the evening is at 270 degrees. If we just click on the sun right here, we can click on the sun. And if I click on the sun, Stellarium brings up a little information box, and it shows me that at this moment in time, you can see the azimuth and elevation, or azimuth and altitude of the sun right here. So in this particular case, on June the 14th at 4:01:30 in the afternoon, its azimuth is 259 degrees, 48 minutes, and then you can see it changing there. And then its altitude is 51 degrees, 30 minutes. The altitude, remember, is measured from the horizon straight up. In Stellarium, you can do this with a little measurement tool. There is a little angular measurement tool in Stellarium down here on this bar at the bottom. It looks like a little angle. If you don't see that measurement angle tool, you can come over here to the menu on the left-hand side. Let me click out of that for a second. You can come over here to this menu on the left-hand side and come down to the little wrench, which is the configuration window. Click on plugins over here, and then one of the first ones there is the angle measure. If you would like to use the angle measure tool, just click this load at startup right here. And then every time you start up Stellarium, it will load it. You might have to exit out of Stellarium and restart Stellarium to get the angle measurement tool to appear. But let me bring up the angle measurement tool real quick. We said here that the sun had an altitude of about 51 degrees, 19 minutes. It's getting lower and lower in the sky as time goes on. Let me use my little angular measurement tool here. And in this case, I can't see the true horizon, so I'm going to have to eyeball it. So I'm going to start right here, and I'm guessing that's the true horizon, and go up to the sun. And we can see that the sun right there is about 51 degrees up in the sky. So that is the altitude of the sun, 51 degrees. If the sun was due west over here, its azimuth would be 270. But you can see that the sun is a little bit to the left of due west, which means its azimuth is a little bit less than 270 degrees. And as we saw, it's 260 degrees over there. So that is the altitude and azimuth of the sun. And of course, if I speed up time here and let the sun set, we will eventually see that the sun sets once its altitude reaches 0 degrees. So let's see. So that is right around the time of sunset right there. It's got a little bit further to go. Okay, so that is the concept of altitude and azimuth. And as I said, the problem with altitude and azimuth is that they're constantly changing, not just for the sun, but for the moon and the stars as well. Because as the Earth rotates on its axis, the sun, the moon, and the stars all rise in the east, move across the sky, and set in the west. And so the altitude and azimuth are constantly changing. What this means is that if I'm in one location of the Earth and I call up another astronomer in another location of the world and I say that there's something that I want you to look at and I specify the altitude and the azimuth, it won't be the same for them. Different observers in different parts of the world see the sky differently. And that's why in our next lecture, we're going to talk about longitude and latitude and talk a little bit about how we measure our location on the surface of the Earth, because how we see the sky depends on where we're located. So please join me in lecture 4, where we will talk about longitude and latitude on the Earth.